Okay, so it's usual for any electricity course, whether that's year 9, year 10 or year 12, to start with some discussion of electrical quantities. And so this will probably be the first one in a series of videos. Now, let's just start with a quick mention of circuits. It's not really a talk about circuits, this one, but you know that a circuit has a power supply, and then generally some sort of device. I've drawn a resistor here, and my power supply I've drawn as a cell. And our circuit is then described by a few important quantities. And the two really important ones are the current which is flowing, which is denoted by an I, which I'll talk about a bit later on. And we always draw the current as running from positive to negative. So the long side on the cell symbol is the positive side and the short side is the negative. And so we always talk about current as flowing from positive to negative. Some of you may well be aware that actually what happens is the electrons flow from negative to positive in most electrical circuits. And this all comes about because Benjamin Franklin, who did some of the really early work on this, simply took a guess as to which way things were moving and which side was positive and which side was negative. He got his guess wrong, and so we deal with that by putting a minus sign on the electron. So we say the electron has a negative charge. So I'll draw E negative. The electron has a negative charge. So the electrons are actually flowing this way, but we treat the current as flowing that way. And in physics, putting a minus sign on something means that it's going in the opposite direction. So that's why there's that negative value for electrons. Putting a minus sign on the electron tells us that they're going in the opposite direction. So slightly complicated, but we always deal in physics with conventional current and not the actual direction that the electrons are going. So going that way, not the red line that I've deleted there. And the way that a circuit always works, or certainly a DC circuit will always work, is that we have some sort of supply. There's my cell. My cell is providing a source of energy. If it's a cell, then that source of energy is going to be a chemical reaction. There's a chemical reaction which wants to complete, and the easiest way for the chemical reaction to complete is to send electrons through the external circuit. Unusual way for a chemical reaction to complete, but a cell is designed so that it's not easy for it to complete. Sort of, the normal way the atoms meeting each other, etc. It's designed so that the easiest way for the cell to complete its chemical reaction is to push the electrons around the outside, and that provides the electrons with some energy. So when the electrons pass through the cell, some work is done to them, they gain some energy, and then when they pass through devices like our resistor here, they lose some energy on the way around. And this can only happen in a complete circuit. The electrons for the chemical reaction to be able to complete in this case, the electrons have to be able to get from one side all the way around to the other side and complete. But do remember, I'll mention this again later as well, it's not as sort of some people imagine, sort of a primary school way of thinking about this is a handful of electrons start out here and move along and along and go a bit further, then go through the resistor and get rid of their energy, and then move out the back and go around. What actually happens is the moment we complete the circuit, every single electron that is able to move in the entire circuit and in the resistor will start to move. The whole lot of them go into motion the moment that the thing is created. It isn't a pile setting out from our cell and tromping all the way around until they get back to our cell and get some more energy. Every single electron in the entire circuit goes into motion at the speed of light, and that's because electrons have a thing called an electrical field, so they all push on each other because of this electrical field. So as soon as we connect the cell, essentially they all know about it because they all push on each other with their electric charge, with their electric field. Now, charge is a really difficult idea. Yeah, it's simple enough for us to say electrons have a negative charge and protons have a positive charge, and you perhaps already know that opposite charges attract. So our electron will be attracted that way and our proton will be attracted that way because they've got opposite charges, whereas if we had a pair of electrons, they would repel. Like charges repel. And so charge is a quantum number. No, we're not going to talk about quantum numbers till we get to year 12, but charge is a number which tells us how the electromagnetic force is going to react, how this push and pull, this push or repulsion, how is that going to behave? That we're told how that's going to behave by this thing called charge. And so charge is a number which tells a fundamental force, a fundamental building block of the universe, how to behave. And it turns out that that charge is incredibly useful for us. There's lots of other quantum numbers and there are other forces, and not all of those forces are technologically useful to us. But this one is technologically very useful to us. Now, for the next couple of them, I'm going to talk about how we measure it. Well, there is a thing called a Coulomb meter. We can measure charge. We don't normally measure charge. When we're doing electrostatics, we might want to demonstrate that we've got a charge or that we've got a charge imbalance. We've got too many electrons or too few electrons in a particular bit of metal or whatever. And that imbalance is shown up with a thing called an electroscope. And so when we do static with you, we may well come across a thing called a gold leaf electroscope, which demonstrates when there is a charge. So charge imbalances are demonstrated with an electroscope. Now, in an equation, the symbol for charge is Q, and there's no hard and fast rules for this, but I tend to use a large Q when I'm talking about a lot of charge, and a little q when I'm talking about a small static charge. Again, that's not really important at GCSE or year 9, but becomes important when we get onto A level. Now, charge is measured in coulombs. French scientist Coulomb was the first one to demonstrate the law of attraction and repulsion and the maths behind it. And so he gets the unit for charge named after him. So has a capital C because Coulomb was a real person. Now, electrons are tiny, impossibly tiny, almost impossible to get your head round how tiny electrons are. Right, I'm just in motion because my cat's locked in here with me. So electrons being absolutely tiny, unimaginably small, the charge on one electron is minus, we've talked about the minus sign, 1.6 times 10 to the minus 19 coulombs. Now 10 to the minus 19. That means we've got to put 19 zeros in front of that 1 and the 6. It's tiny. One electron is a minuscule thing. You just can't think how small it can be. There's no way you can think about it. And therefore, to have a coulomb's worth of charge, 1 coulomb, then we've got to have 6.25 times 10 to the 18 electrons if it was a negative coulomb's worth of charge, or protons if it was a positive coulomb's worth of charge. Again, they're so small that you can't get your head around how big that number is. I think that billions of billions, so that's 6.25 billion billions, I think. Charge, positive and negative, determines how the electromagnetic force acts, measured in coulombs, but we never really actually measure it. We know it's there, we know we can do calculations with it in circuits and things, but we don't ever actually measure charge. Current, on the other hand, we measure all the time. And So in our circuit, we'll want to know what current is going around our circuit, so we put in an ammeter. And the ammeter needs to be part of the circuit, measured with an ammeter. There's my symbol for an ammeter, a circle with a capital A in it, and the ammeter has to be part of the circuit, so that the current will actually flow through it. The analogy is to the flow of water in a river. You can imagine measuring how many cubic meters of water go past a point in a set amount of time. Well, that's what an ammeter is doing. It's not literally counting them, it's counting their effect, but it is measuring how much charge is flowing per unit time. It's measuring the rate of flow of charge. So the ammeter has to be in the circuit, has to be part of the circuit, so that that charge actually flows through it. If the ammeter was external to the circuit, then the charge wouldn't flow through it. So we've got to have the ammeter actually as part of the circuit. Now the ammeter, that means the ammeter has a possibility of disturbing the circuit, so we have to work hard to design our ammeter so that it has as little effect on the circuit as possible. It's just doing a measurement, it's not actually changing the circuit. It's not 100% possible to do, but you can get very, very close. Now this is the difficult bit. I find the word formulae difficult. I feel it should be formulas, but we all have to use these funny Latin endings. So it's the symbol when it occurs, when we want to write current in a formula, we use the symbol capital I. Why do we use capital I? Well, because the chap who first did the calculations on this was called Ampere, and he imagined the current as the intensity of electricity, and so he used I for intensity. And so in order to honour him, in order to stay true to his original thoughts, we use I in formulas to represent intensity. And so there's the formula. It's the rate of flow of charge. So it's how much charge, Q, divided by how much time, T. Or we could rearrange that so that charge is equal to the current flowing multiplied by the time taken. So that gives us our fundamental definition of current and charge. It's that charge is the amount of current multiplied by the amount of time taken, or current is the charge that has passed divided by the time. Unit, as I said, is because of Ampere, who did the early work on this, and so the unit is called an ampere. We all, I certainly do, I do it all the time, we all shorten it to amps. But amps is not actually the unit, ampere is the unit. And so in an exam, if you write amps, you risk not getting the marks, you risk being penalised. So although we'll all say amps, you'll hear me say amps, you'll hear Mr. Smith, Mr. Baker, you'll hear us all say amps. When you write it down, either write amperes or do the physics thing, which is be lazy, just write a capital A. Don't write amps, write ampere or write a capital A. So you remember the definition of what a coulomb was, and therefore 1 amp is 1 coulomb per second, and 1 coulomb is 6.25 times 10 to the 18 electrons. So if my ammeter is measuring 1 amp, that means that 6.25 times 10 to the 18 electrons are passing through that ammeter every second. It's an extraordinary number. Can't begin to imagine such a big number. Okay, so what we can do is we can think about the number of electrons that must be in one of our lab wires. Now, these aren't quite our lab wires in the picture, but they're the closest I could find from a quick search on the internet. Now, the wire, of course, is copper. What you see is the plastic exterior, and the plastic exterior is just there for insulation, and the two different colours are just there to help with building the circuit properly. Now, the interior is copper. It's copper that's conducting the electricity. Copper has 29 electrons to each atom. But only one of those electrons is what we call delocalized. You remember in metallic bonding, the metals share their outermost electrons with all of the other metals, and those outermost electrons become free to move. Well, in copper, only one per atom is shared. all the rest of them stay bound. So the other 28 stay bound to the copper atom, and 1 is shared. And delocalized means no longer in one local area, it means it's free to move about. So our metal can conduct electricity. Now, 1 cubic meter of copper has an enormous number of atoms, 8.5 times 10 to the 28. Now, you can work that out by using a thing called Avogadro's number, which is the number of atoms in a mole, and by the density of copper. But neither of those two things are on the physics course, and so I just looked that number up on the internet. And of course, we know how many copper atoms. We also know how many delocalized electrons there must be in that cubic meter of copper, because it's 1 per atom. And so therefore 1 cubic meter of copper has 8.5 times 10 to the 28 electrons that are free to move around and conduct electricity. So how many electrons that are free to move around and conduct electricity? Sorry, I'm coughing. My wife is burning sausages. How many electrons are there in our bit of wire? Well, to be able to work that out, we need to know what the volume of the wire is in cubic meters. Now, I've said that the interior of the wire is 2.5 mil thick, and that on average those wires in the lab are 30 centimeters long. And you remember from your maths that the volume of a cylinder is the cross-sectional area multiplied by the length. So the volume of my area, because it's a cylinder, that's a circle. So that volume, the area is given by pi r squared. So pi times. But of course, I've been given d, so I've got to remember to halve it. So 2.5. Now that must be in meters, so I'm going to put times 10 to the minus 3. I use times 10 to the minus 3 because on your calculator, putting times 10 to the minus 3 in is really, really easy, and that instantly transforms it into meters. Times 10 to the minus 3 means thousandth, so 2.5 thousandths of a meter. Half that to make it a radius, square it. There you go, there's my cross-sectional area, and then I'm going to multiply that by my length, which is 300, but I've also got to put that into meters, so 300 times 10 to the minus 3. Now, if we put that into a calculator, that gives us our volume, and our volume turns out to be 1.47 times 10 to the minus 6 cubic meters. So that's 1.5 millionths of a cubic meter. Not very much, but then they're not very thick wires. Now, what do I got to do with that then? Well, of course, if there are 8.5 times 10 to the 28 atoms in a cubic meter, and I have this many cubic meters, how many electrons are there within my wire? Well, I've just got to multiply those two numbers together. So the number of electrons is equal to the number of electrons in a cubic meter multiplied by the number of cubic meters I have. And if you put that in your calculator, that comes out at about 1.25 times 10 to the 23. Just over 1 with 23 zeros after it. An enormous number. That's the electrons in one of our lab wires. You know those little wires that we use in the lab all the time? The electrons in one of those wires. 1 with 23 zeros after it. Electrons are really, really little. Now, we can extend this analysis a little bit by asking the question, if we put an amp through our wire, so if we have a PD across our wire and we have an amp flowing through it, so the electrons are all going that way, then 1 amp is 6.25 times 10 to the 18 electrons every second. So the question I've asked is, if there's an amp flowing through my wire, which is quite a lot of electricity, an amp is flowing through my wire, how long will it take for every electron which started off in the wire to flow out one end? So we've got electrons, I'm not going to draw 10 to the 23 dots, and our electrons, we put a voltage on, our electrons all start to move. How long does it take for every electron that started off in that wire to move all the way through the wire and out that end? How do we work that out? Well, it's relatively straightforward. All we've got to do is we've got to say I've got that many electrons and divide through by how many of them move every second. that many of them move every second. So if I do that division, I get an enormous number, 20,000 seconds. Just over 5.5 hours. So it's amazing. If I have 30 centimetres bit of our copper wire, I put an amp through it. An amp's quite a big current. I put an amp through it. How long does it take for all the electrons that started off in that wire to move out of that wire? And the answer is 5.5 hours. Now you mustn't think I've emptied the wire. If I left it attached for 5.5 hours, you're perhaps thinking I've completely emptied the wire and there's no electrons left. But of course, because it's a circuit, it's always joined together in a circle, which means that the electrons that are leaving out of this end are being replaced by new ones coming in from this end. So I don't actually empty the wire. But how it takes 5.5 hours for all those electrons, even though an amp is 6.25 times 10 to the 18 electrons passing every second, it still takes 5.5 hours to shift all the electrons in my 30 centimetres of wire. And of course, because to shift them all, that means I've got to take the one that's right over this end to start with and take it all the way through and all the way through and all the way out. That also means that in total they're going to have moved 30 centimetres in 5.5 hours, which means that our electrons are travelling at 5.4 centimetres an hour. Not very fast. It's not actually quite true. They're actually moving really, really fast, but they're moving fast in all sorts of random directions because they're hot. They're bouncing around all over the place like nutters because they're hot. Just that when we put a voltage on average, they'll end up moving, drifting, because you see it's only very slow, so it's called drift velocity, drifting in that direction because there's a voltage giving them a push. It's 5.5 hours. The numbers and the ideas involved in this electricity are extraordinary. Luckily, for most of what you do at GCSE, you don't actually have to think about these enormous numbers. You just call it 1 amp. And then your maths is based on 1, not maths based on 6.25 times 10 to the 18. Now, I've said this a couple of times now, an amp is actually quite a lot of current. If you try to pull more than 9 amps from our power packs, they'll cut out. They've got a little overload thing and they'll cut out. They won't produce more than 9 amps. They're not up to it. But actually, them producing 9 amps is a lot. If we think about things around the house, a kettle might draw 9 or 10 amps. A hairdryer varies a lot from a hairdryer to hairdryer, but I said on average or something like 6 amps. A desktop computer, a couple of amps, might draw 3 amps if you've got a really super duper game playing machine that was working really hard to render some 3D game where you were shooting people. A large TV, modern ones actually, hardly use anything at all. Just over half an amp. And a phone charger down into hundredths of an amp, 200ths of an amp for a phone charger. So it's only things to do with heat. Kettles heating water up, hairdryers heating air up. It's only really things to do with heat that are pulling a lot of current. Anything to do with electronics is going to be down at this kind of level, apart from your desktop computer, because there's just so much electronics going on within your desktop computer, all of them pulling current, and so that pulls a bit. But as a general rule, big currents involve a lot of heat. As a consequence, big currents will get a resistor really quite hot. So you'll probably notice that when you do experiments involving resistors, is that the resistors heat up very fast, and you have to be careful of them or you burn yourself. And if you run a big current for any length of time, you'll even get the wires hot. Even though we've got 2.5 mil wires, are actually quite thick wires. And copper's very good at conducting electricity. Even allowing for all of that, the wires themselves will get hot because an amp is a big current. Typically, with smaller currents, we tend to use milliamps. And for all electronics, milliamps would be the kind of regime we'd be working in. We would not be working in amps. We'd only be working in amps when we're talking about heating things up. We'd be working in milliamps for most day-to-day uses of electricity. But Your course doesn't really recognise that, so most of your course calculations tend to be done in amps rather than milliamps, but I suspect some of the examples you'll get thrown will be milliamps. Okay, potential difference. Well, if I sort of scribble a circuit again, potential difference is always measured as a difference. So our voltmeter, there you go, symbol for a voltmeter, is measuring the difference between that point there and that point there. So it's always external to the circuit. It's always measuring across two things, trying to measure the difference from one place to the difference to another place. So voltmeters always external to the circuit, measuring a difference, which is why potential difference is a better term than voltage. Even though voltage is fine, potential difference is the better term because it reminds you, it's supposed to get in your head that what a voltage is, it's always measuring a difference, and therefore a voltmeter has always got to be connected in two separate places so it can measure the difference between those two separate places. Now, what is potential difference? It's the work done by a coulomb's worth of charge. Now, work done, you might remember, is converting an energy from one form to another. And so it's the conversion of energy or transfer of energy by a coulomb's worth of charge flowing. 6.25 times 10 to the 18 electrons flowing will do the work, to do the work. So if we have 1 volt, we'll get 1 joule of energy being transferred when 6.25 times 10 to the 18 electrons, or 1 coulomb's worth of electrons, flow past. So it's the energy transferred per unit charge. It's measured with a voltmeter, as I've mentioned already. Its unit is volts, named after Volta, who was a Italian physicist. And so volts, named for Volta, are always going to be a capital V because Volta was a real person. Now this causes confusion. It's the only one I can think of where the symbol in the formula is the same as the symbol for the unit. Now you'd think that makes things easier, but for some reason it tends to confuse you all. I think you think, well, it's true for volts, so it must be true for everything else, and you start putting A in for current when you should be putting I, or R in for, ohms in for resistance. It gets you confused. It's the only one I know of where the unit and the symbol are the same. Think about distance. We might rewrite D in the formula, or S sometimes, but the unit is M for meters. Nothing else has the same for both of them. You can tell them apart when they're written down, when they're typed, because when they're typed, the one that's the symbol for the formula should be italic. Can you see this one's leaning over slightly, whereas that one is upright? And so the unit should be upright, whereas the symbol, which to represent some value V in a formula, should be italic. I try and remember to do that when I'm doing these things. Mr. Smith, Mr. Baker, they try and remember. We don't always get it right. Your exam board do always get it right. It will always be italic when it's representing a voltage that's going into a calculation, whereas it will be upright when it's representing the unit volts. And there's the formula. Work done is an energy, so energy divided by the amount of charge. Energy transferred per unit charge. So to get that, we get the total energy transferred divided by the total amount of charge that's flowed, and that gives us the voltage or the potential difference. Okay, just to think a bit more about potential difference, the easiest way to think about potential difference is to think of it as being the push. It's the push that's shoving the electrons around the circuit. Bigger the potential difference, bigger push the electrons are receiving, and in general, the more electrons that will flow for a bigger potential difference. So the potential difference is the push shoving the electrons around the circuit. It can also be thought of in terms of energy, because you saw the definition was all about energy. So I'm just going to talk it through in terms of energy. You don't need to be able to reproduce this. You just need to be able to sort of think through some of the ideas. So if I quickly sketch a circuit, cell, resistor, and I'm going to put a voltmeter across is the correct terminology, across the resistor. And it's always across because the voltmeter is measuring the difference between the energy potential of the electrons there, how much potential the electrons have got to do some work there, compared to how much potential do the electrons have to do some work there. So it's measuring the potential difference between 0.1 and 0.2. And so it's always a potential difference. Now, what's going on here? Well, our cell has a chemical reaction running through it. Chemical reaction is set up to be frustrated. There's a barrier in the way. The chemical reaction can't complete. Chemical reaction wants to complete. Chemical reaction can't complete. And the simplest way for the chemical reaction to complete is, instead of trying to have the electrons and things meet in the middle with a barrier, is to shove the electrons around the external circuit. You've probably never thought about chemical reactions in this way before, but a chemical reaction is just a transfer of electrons. Yeah. Sodium gives up one of its electrons over to the chlorine. You've made sodium chloride. You've made salt. A chemical reaction is just a transfer of electrons. Now, if you put a barrier in the way so it's not easy for them to transfer their electrons, the chemical reactions can still complete, providing there's an external circuit and they can push the electrons around the external circuit. And so that's what a cell does. Chemical reaction, and because it's a chemical reactions are energetic. You might remember us doing it, making a sort of little model cell with two different metals, and those two different metals had two different reactivities. And so one of them was much more reactive, much more likely to want to complete. One of them is going to be much more greedy for the electrons than the other one is. And so there'll be a difference between them, a potential difference between them, an energy difference between them. And so our cell has an energy difference between the two sides that represents the energy involved in the chemical reactions going on within the cell. Now, wherever we have a chemical, an energy imbalance, what we get is that nature really wants to wipe that energy imbalance out. The analogy I quite often use is a mountain with a rock at the top. That rock being very high at the top of a mountain is an imbalance. It's a long way from the equilibrium level. The equilibrium level is down at ground level. But eventually, we all know that rock will get down to the bottom. That rock will get down to ground level, and even over geological time, the entire mountain will get down to ground level. Everything wants to get down and level down, and so our cell is providing us with an energy imbalance. Our electrons are going to try and wipe that energy imbalance out by marching around our circuit. So our electrons, I know the electrons go the other way, but we'll do it in terms of conventional current. Our electrons, or our current, better, our conventional current is going around our circuit, and we'll keep on going round and round our circuit, keep on spending this energy that the cell is providing until the cell is no longer able to provide any energy. The cell runs out, we'll stick it in the bin, or we recharge it, depending on what kind of cell it is. Now, the electrons, as they move, use up some of that energy. The current, as it moves, uses up some of that energy. Now, we don't tend to worry about the energy use in the copper wires. If we've used thick copper wires, the electrons slide through those thick copper wires really easily. There's plenty of electrons to carry the current. We've done that maths already, and copper doesn't provide much opposition to the flow of those electrons. And so we don't worry about any energy being lost in the copper wire, even though some is. We don't worry about it. We don't take it into account when we're doing our calculations. But a little bit of energy is going to be lost in those copper wires. And I've mentioned already that if we run an amp through a copper wire for long enough, that bit of copper wire will start to get hot because energy is being transferred to the copper wire. But the majority of the energy is used up in pushing the current through the resistor. The job of a resistor is to resist. And so shoving the electrons that slip easily through the copper, shoving them through the resistor, a whole lot harder. and consequently the resistor gets hot. And so what we have here is we have an energy transfer due to the electricity. Energy starts off as chemical energy within our cell, and it ends up as thermal energy in the resistor. The energy is transferred from cell to resistor. Work is done to the resistor. Consequently, the current here has energy. The current here has spent that energy, has done the work to the resistor, has spent its energy. And therefore, there is a difference between the two of them, and that's what our voltmeter is measuring. Our voltmeter is what's the difference in potential of a coulomb's worth of electricity here compared to a coulomb's worth of electricity there, it having spent its energy going through the resistor. The energy that comes out the other side, the electrons that come out the other side, well, they have to complete. We can't get the electrons mounding up in one place because they repel each other, so that's not allowed. You can't. They'll have to keep on going around the circuit. They can't pile up in one place or another because they're all pushing out very hard on each other. They're all repelling, and so our electrons will, our current will complete, go all the way around our circuit. And so the electrons, as they come out here, have got just enough extra energy necessary to push them around that last little tiny bit of copper wire and get back to our cell, where the chemical reaction completes, and consequently the electrons that come back out over here have had some work done to them by that chemical reaction completing, and so they've gained some more energy, and it's just then available for them to spend in the resistor, getting the resistor hot. They've got no energy, they come back here, they pick it back up again by a chemical reaction completing, they come round, they spend it in the resistor. Okay, so the resistor is having work done to it by the motion of the current. The cell is doing work to the current in pushing it from having run out of energy this side up to back up to having energy on that side. And our electricity, our flow of electrons, trying to wipe out this imbalance that's been introduced by our cell, spends itself by heating up the resistor. So potential difference is the difference in the potential to do work of electrons in one place compared to another place. Now, sticking with this idea of potential difference, we'll just touch upon parallel circuits. You can do more parallel circuits later on, but if we touch upon if I quickly sketch a parallel circuit. One of the things that it's a good idea to get your head around is the fact that because we don't treat wires as requiring any energy to be spent in travelling through them, you know, we know in the back of our minds that a little bit of energy must be spent in travelling through the wires, but actually we don't bother with that with the maths of that, because we don't treat wires as spending any electricity. Any wires that are joined together are going to be at the same potential. So if our electrons, or if our current rather, not our electrons because they're going the other way, if our current is starting out there, coming down here, splitting off, some of it's going that way, some of it's going that way, none of it has spent any energy so far. And so all of those points there, every point along that wire, all those bits that are joined together there, will all be at the same potential. Similarly, over here, we know they've got to have just enough energy to get back to the cell. And as we don't count that as there being anything worth thinking about, we know that over here, they've got next to no energy. So over here, all of these wires that are joined together are also at the same potential. So I'm going to say these ones are at potential 1, and I'm going to say these ones are at potential 2. Sorry about my writing on my screen. Therefore, it doesn't matter where I place my voltmeter. So if I place my voltmeter there, the potential difference is measuring is the difference between potential 1 and potential 2. If I place a voltmeter there, the potential difference is measuring is the difference between potential 1 and potential 2. If I place a voltmeter there, the potential difference is measuring is the difference between potential 1 and potential 2. If, on the other hand, I place a voltmeter here, the potential difference that it's reading is the difference between potential 2, and potential 2. So our voltmeter will read 0 volts because there is no potential difference. Same if I put a voltmeter over on the other side. I put a voltmeter between there and there. That's still potential 1 at the top and potential 1 at the bottom. There's no difference, and so my voltmeter will read 0 volts. So the other thing about potential difference that I'd like you to remember is that wires that are joined together with no device in between, a cell or a resistor or a lamp or whatever our device might be, wires that are joined together are all at the same potential difference. They're not quite at the same potential difference because there's an energy required to move through the wires. But it's so close to being the same potential difference that we don't worry about it. We say they're at the same potential difference. And if you remember that, a lot of the stuff that we do with parallel circuits and solving parallel circuits makes more sense. Okay, so in summary, we don't worry too much about charge. We know it's there. We know the electrons have a charge. Therefore, they're all repelling each other. They're all pushing on each other, trying to spread themselves out nice and evenly around the circuit. But we don't worry about it too much. We've got to know that it's recorded in coulombs, but we never measure it in a circuit. We work out what's going on with charge by working out what's going on in current and time. Because current is the rate of flow of charge. So if we know the current and we know the time taken, we can work out charge. We don't measure it directly. Confusing thing about current is the use of I as its symbol in formulas, but that's easier to understand if you remember that the Frenchman who first worked this out thought of it as current as intensity, electrical intensity, hence I. We don't. We talk about it current because that makes sense in thinking about the analogy with the flow of water in a river. It's measured with an ammeter. I sometimes see people writing amp meter with an extra P in there. The P is dropped. It's an ammeter. And it's measured in amperes. Remember that the full unit is ampere. Everybody says amp. I've said it all the way through this video. But if you write it down, you've got to write down amperes. So don't write it down. Write a capital A. Now, a bit long this one. Current is usually a flow of electrons. Almost always it's a flow of electrons. It's not quite always though. We did an experiment where we measured the current flowing in salty water, and there the current was being transferred by, the charge was being transferred by ions of both sodium and chlorine. But most of the time, certainly in sort of when we're using wires, the current is carried by the electrons. And so because current is the rate of flow of charge, it's also the rate of flow of electrons, and that's the easiest way to think about it. Your electrons are a great big river, quite a slow moving but absolutely massive river of charge in motion. And so, as we've briefly mentioned with the calculations, you remember you don't have to be able to do those calculations, but we just went through some of the numbers. It's unimaginably large numbers of electrons in motion, and consequently, they usually move quite slowly, even though the effect is enormous. Lighting in your house, maybe the heating in your house, the operation of every bit of electronics you own is all about those electrons moving about. So the effect is enormous. But they're not moving very fast to do it. There's just so many of them. And potential difference is the push, the simplest way to think about it. It's not a very scientific way to think about it, which is why I've written that in italics. So it's not very scientific, but it is the simplest way to think about it. The potential difference, the voltage, is the push. Usually, the bigger the voltage, the more electrons that are going to be in motion, or the faster the electrons are going to be moving. We have this confusing thing where the symbol that we use in a calculation is V, capital V, and the symbol we use for the unit is also capital V. The only quantity in physics I know that's like that. And we always measure voltage across 2 points. And finally, potential difference is the energy transferred when 1 coulomb's worth of charge flows through a device. So electricity is transferring energy. And so the potential difference is a measure of that energy transfer. And so we know how much energy is being transferred into a resistor if we know what voltage is across a resistor and how much charge is flowing through that resistor. So potential difference is a measure of the energy being transferred. But as I say, the simplest way to think about it is the push. If there's a big voltage across a resistor, that means there's a lot of push being applied to that resistor. If not a lot of current is going through, despite the fact you've got a big voltage, then you know that that resistor is doing its job very well and is seriously resisting. It's a big resistor. And so that completes this summary of the major quantities, those quantities being, just sort of once again, charge, current, and potential difference. There is, of course, when we're talking about circuits, one more really, or certainly DC circuits, there's one more really important quantity, and that's resistance. But we'll go on and talk about resistance in a different lesson.